Okay, so now we have the final exercise of this exercise sheet. They're giving us the situation where we get are presented with a unfair coin with a probability p in from the range of 0 to 1 that we get heads. We throw this coin n greater than or equal to 5 times. Here we don't have to do that define the events so exactly like in exercise 3. We're gonna denote heads with 0 and tails with 1. So let's just write this information. So unfair coin, oops, unfair coin where p 0 to 1 it for heads. So the probability of us getting heads is gonna be unfair. That means not 1/2, and it can be from 0 to 1. Then we're gonna take that we throw this n times, so n greater than or equal to 5 tosses, and we're gonna denote that heads are denoted as 0, and tails are denoted as 1. That's it. So now they're asking us to give the probability space, right? So the probability space is defined by these two little things. So we have to define those two little things. We're gonna first start with omega. Omega can be either 0 or 1, or heads or tails, right? So we can do heads or tails for each throw. And as we're throwing it n times, we're going to do this with the power of n. This is equal to 0, 1, n. So that's pretty much what we want. Now the next case, right, is going to be, oh my gosh, what did I do? We're going to denote the following. Let me just open a note real quick. No, this is not it. Where's my notes, man? Did I lose it or something? I think I just did. I could have lost it actually. Whatever. Doesn't really matter. The point here is that we want to denote now the probability, right? So the probability of, say, W, and we denote W as being any amount of W's. It's not really W, it's omega, but I call it W because it's easier. Can be followed by saying, well, the probability of getting all of these, right? So all of these. And as we know, each throw is independent. So if it's independent, we can just write the following, right? It's going to be a multiplication up till n, right? So now let's just see what it means to just get one, right? Just one throw, so to speak, one omega. Let me just put this over here, right? What does this mean? Well, just denote what it means to just have one throw. So imagine we have Wi. Wi means, just simply put, we're going to multiply p, yes, and we're going to have n throws, so it doesn't matter how many n's we have. So in this case, we're going to think about it, and we're going to take n, n, so we have n throws minus whatever w is in this case. So let's just say, how can I explain this better? It's a bit confusing to explain, but it's really not that difficult. So we denoted this, right? I'll just explain it like that. Oops, I'm getting totally confused over here. Which one is this guy? Is this guy, yeah. So we already stated that this is going to be just independent cases. So what's the probability of us getting a heads? The probability of us getting heads for any I is gonna be just, well, getting heads. It's gonna be, only let's just rewrite this, of heads is the same as saying the probability of Wi or omega I being equal to 0, right? So what's the probability of that? Well, simply put, we know that's gonna be P because we already stated this. We already stated that this is gonna be P from 0 to 1 for heads. So let's just write that. Now, in the opposite case, what's gonna be the opposite of this? Is a complement rule, right? So the complement of heads is gonna be tails, and the complement of that, hold on, the complement of that is gonna be 1 minus P, right? Or 1 minus, well, if you wanna go really mathematical, 1 minus this guy, which translates to 1 minus P in this scenario. So now that we have that, we want to conjoin them. We want to join them together. So how do we do that? Let's go back to the note we already have here that I already wrote. Oops. If I can find it, that is. So in this case, look at this. N is going to be, if we take N minus the number of tails that we get, that's going to be, simply put, N minus, right, the amount of tails that we get, in this case is going to be this, is going to give us a heads. Therefore, we can denote as this being the number of tails. Now, why is this so? Why? We want to understand that. Well, if we go back to our exercise, the original one, not this one, I think it was this, yeah. We know for a fact that tails is equal to 1, right? So we can just write this. This is equal to 1. Therefore, whenever we get a 1, it means, well, simply put, we're getting tails. So, N, imagine we have 5 throws and we got 3 tails. Then we're gonna get 2 heads, right? So we want, in order to denote this, it's gonna be the number of, the number of, how you call this? I totally forgot, of heads, right? So if we want to just do this, we're gonna do this, up to 5, Wi. And Wi is, well, omega I works because we only have 0 and 1. So if we just add ones, that's gonna be, simply put, our tails. So this is gonna be equal to the number of heads. Therefore, the number of tails is given, right? Simply put, by, well, this little guy, right? So if we want to find the probability of whatever, right? Simply put, it's going to be just a multiplication, as you can see, right? This is going to be the multiplications, independence. So if we want to find all the probabilities, we'll duplicate this little guy. And this is going to be equal to P, right? Which is for our heads. And how many heads do we have? Well, it's going to be just N minus, well, this. We can just copy it, duplicate it. We don't even have to write this. We can just put it over here. And then we do 1 minus, and then this little guy over here. And that's simply going to be the number of, so to speak, things. And we have finished denoting our probability space, right? That's it. That is pretty much it. We're done with A. It was a bit confusing. I was trying to explain it in a more detailed way, but that's pretty much it. because it's 0 and 1, we can just count all the omegas, and the summation of the omegas is going to be simply the number of tails, because that's equal to 1. So we can just ignore that, you know? So yeah, that's pretty much it for A. Okay, now we have this exercise. So we want to calculate the probability, yes, that we get the third head before the second tail. Now we know for a fact that tails are equal to 1. So if Wi1 is equal to 1, W2 can be equal to 0. Though you know what I mean, right? Each toss can be either 0 or 1. In this case, that's it. So we want to find a number where we get, simply put, a value that's less or equal to 1. We cannot do 2. So what we'll do is saying, we know for a fact that whenever we get heads is 0. So we add 0 plus 0 plus 0 plus 0 plus 1. We got, in this case, as you can see, we got the third head before the second tail. We only have one tail, right? We can also have, for example, 0 plus 0 plus 0 plus 1 plus 1, right? In this case, we also got 3 zeros before 2 ones. We can also do 1 plus 0 plus 0 plus 0, or yeah, plus 1. In this case, we've got 1 tail and 3 heads, but that was another case where we get less, we get all the heads that we want before the 2 tails. So how do we calculate this? If you see, whenever this is actually true, right? In this case, for example, it's going to be equal to 1. In this case, it's going to be equal to 2. In this case, it's going to be equal to 2. So whenever we have something that's, so to speak, it works, like definitely will work, is whenever we have equal to 1. Because if we have 2, it could come to the case where it works, but we don't want that. So what we do is saying, instead of focusing on 5 tosses, let's just focus on 4 tosses, because the thing that's limiting us is the 2. So we're going to remove one of these tosses, and we're going to focus only on 4 tosses. And whenever we have 4 tosses, you can see we always get 3. We can always get this logical sense of getting 3 heckin' heads before 2 tails, because that adds up to 4, you know? So that event is going to be event A, where omega is part of omega, right? And simply put, such that W1 plus W2 plus W3 plus W4 are lower or equal to 1. In this case, the W's are going to be the tosses, and 1 is like our limiting factor. We cannot go more than 1, because if we go more than 1, it won't work in 4 tosses, you know? So, taking that into consideration, we can do the probability of A, right? What is the probability of A? Well, simply put, in this case, we know for a fact that we're going to have 4 heads, yes? Hold on, let me just think, actually. It's a bit confusing here. So we can take a look and look at the exercise here. Yeah. Okay, so after checking what we're doing, we can simply take all the cases, right? Let's take 1, 2, 3, 4. In this case, we do have at least 3 tosses before the second tail, so that works. Then we have 0, 0, 0, 1, and then at the end we're just gonna do like the usual distribution of how we do with binary numbers, right? And as you can see, and every single time we're going to get 3 heads before the second tail. So in this case, we got to see the probabilities. So in this case, we have 4, and that means we're going to have p to times, p to the power of 4, right? Times 1 minus p to the power of 0, because we have no tails. Remember that what we did here, right? Over here, we said that whenever we get an omega equals to 0, it's going to be equal to p. And whenever we get omega I equal to 1, we're going to get to 1 minus p, right? So we're just working with those probabilities. And because we have 4 heads here, because we have 4 heads here, we're just going to place p to the power of 4. Because they're independent, so we can multiply them. In this case, it's going to be p, and then 1 minus p. In this case, and these are going to be repeating themselves. What is going on with my iPad today? So we can just replace these and duplicate them like so. And then we're going to sum them up. So if we sum them up, we're going to have p4 plus 4p3, 1 minus p. And that is the probability of, simply put, PA. That is it. So yeah, that's how you solve B. So this one is a bit more tricky in the sense that, well, just a bit tricky in it. Here we have the condition where they say that n is going to be even, yes? And we define the following events. So n, A is going to be this, B is going to be this, C is going to be this. And we have to write with words or show B in the counterexample if A is a subset of B, if C is a subset of A, and give also the intersection of A and B, and A, B, and C. So it's a bit, overwhelming, but we just have to go step by step, right? So let's go with A, and let's see what A describes. So they're giving us that W is equal to, well, all the tosses in omega, such that the omega with 2i index, meaning it doesn't matter what I we take, whenever we multiply with 2, any value, any natural number that you take with and you multiply it by 2 is going to be an even number. So it's just saying even sub-index. Or it's equal to 0, meaning that all even sub-indexes are equal to tails. Sorry, to heads. Gosh, I always get confused. For all i's up till in divided by 2. So what does this mean, right? N divided by 2. Well, it means if we have an even n, let's say take n is equal to 6, and we divide it by 2, we're going to get 3, right? So I has to be in the range of 1 to 3, right? So in this case, whenever we have omega 2, 1, there's going to be omega 2, omega 2 and 2 is going to be 4, and omega 3, 2 is going to be omega 6. So as you can see, it says that basically this rule tells us that all sub-indexes where we have an even number, right, we'll have equals to heads. That's it. So we can write here all even tosses are equal to heads, right? The next case, let's read it. Again, same thing, doesn't matter all the tosses. We can ignore that. And it says here that this is a cardinality, meaning the size of whatever set we have. The size of the set for which we have indexes from I to n, where omega sub-index I is equal to 0, is greater than Well, the same thing, but for 1. Meaning that the amount of heads in a sequence is greater than the amount of tails. Yeah? Greater or equal. That's it. That's what we want, because this is what it basically is describing. And in this case, it's saying the following. It says that, well, again, same deal here, doesn't matter. And then it states, there exists no index from 1 to n minus 1, for which, yes, w and wi plus 1 equals to 0. Meaning, there exists no index for which we get two simultaneous, like two, one after another, heads. So we cannot get heads and tails. That will not work in C. That is not going to be part of C, right? So that's no to subsequent, I think it's called, subsequent heads in the tosses. That's it. That's basically what we want. So let's check first if A is gonna be a is gonna be a subset of B. In this case, it's quite obvious that it is. Why? Because imagine, we have even tosses, right? We have always even tosses. When we have even tosses, is going to be equals to heads. And because we have an even number of tosses, we will always have at least the same amount of heads than we have tails. Therefore, this holds also. Maybe we won't have, maybe in A, right? In A, we won't have more heads than tails because n is even, but we will have at least as many tails as we have heads. Therefore, it is a subset of B. Yes. I'm not going to write it because, I already explained it, but that's pretty much intuition. Now let's check the next one, which is saying C, is it a subset of A? In this case, they're asking us if C is a subset of A. And we know that in C, we cannot have two subsequent heads in the tosses. So we cannot have heads one after another. And in A, right, we have all even tosses are equal to heads. So in this scenario, what happens, right? That's a bit more confusing. But let me just check my solution here because I do not remember what I did. If I can find it. Right. Yeah. So let's take a case where there's no two subsequent heads in the tosses. So we could have, for example, 0, 1, 1, 1, 1, 0. In this case, we have, this is actually in C, right? Because we have not subsequent heads, but we do have subsequent tails. And this is not in A. Therefore, C cannot be a subset of A because it has something that A doesn't. So we conclude with that. The next one is saying A and B. Yeah, it's pretty simple. We want to see A and B. Oops. Right? Now, A and B, how does that work? Well, if we look at this and we take another circle here, it's a bit confusing, but this is A and this is B. We know that A is a subset of B in this case, and it will look something like that, right? It doesn't cover all cases, but it covers some cases of B. That's why it's called a subset. So what's the intersection between A and B? It's simply A, because this is going to be intersecting. This is intersection. Therefore, this is going to be A. That's pretty much self-explanatory. Then we have the following, which is going to be A intersection B intersection C. We want a case where all even tosses are equal to heads, right? And because we know for a fact that A and B, A intersecting B is A, we can just rewrite as A intersection C. Is there an intersection? Although they're not, although C is not a subset of A, there's still like some sharing similarities in the sense that we could have, right, the 1 0 1 0 1 0 case, because in this case, right, let's take C. If we take 1 0 1 0 1 0 1 0, this sequence will always have even in the even spots. Yeah, we will have heads, and we also have no subsequent heads in the toss. You see? So in this sense, we can say simply that this would be the set where we have 1 0 1 0 1 0, boom boom boom, and that's it. That is simply it. That's how you solve exercise C. So yeah. Okay, so we're back with this one. Let's say that we have an n equal to 5, meaning we have 5 tosses, and we want to find the probability, the longest series of getting heads, one after another, is 3 or 4. What does this mean? That we have 3 heads, one after the other. So how many combinations do we have of this? Well, let's simply see. First of all, let's say we have tails, tails, and heads. So like that, tails, heads, heads. Tails, heads. We can do the opposite as well, right? Imagine we get the heads first and then the tails. Then we can also get that we get one tail, one tail, one tail, 3 heads and 1 tail, yes. And you would think that's all the cases, but we can also get only 1 tail at a time. So we could have 0, 0, and then 1, 0, 0, 0, or we could have 0, 0, 0, 1, 0, right? So in this case, we have, as you can see, 5 different cases whenever we have 3 subsequent heads. So how do we calculate this? Well, we only see the p's. We know that these are p's, and these are 1 minus p. As they're independent cases, we can multiply them, and then we can sum them all up. So, meaning this will be, we have 3 heads, so p to the power of 3, 1 minus p squared. Same thing over here, because we have this, it's the same thing, just a different order. Same thing over here, same thing, different order. In this case, it's going to be a bit different because we have p4, 1 minus p, and this is going to be the same case. Now, whenever we have 4 heads after another, let's see what happens, right? We can have first the tails and 4 heads. Then maybe the 4 heads come first. And yeah, that's all the combinations we have. Therefore, we get, p4, 1 minus p, p4, 1 minus p. Then we have to sum the common terms. So we sum all the common terms. In this case, we have 1, 2, 3, 4. So we're going to have 4 of these if we sum them up. And then we get the 3 ones, 1, 2, 3, which we have 3 of. So let's just copy this, duplicate it, and then we sum them up. And this is going to be the probability that we get P 3 heads or 4 heads. At one after another, obviously. That's it. That's as easy as that. So yeah, that's pretty much how you solve this exercise. Remember that it's confusing, but you just have to go with the definitions they give you. So coming back to A, I think that was the most confusing part for me at least, was to understand that they're independent situations, so we can multiply them. And whenever we want to model all the possible cases, we have to find the case one and then case two, which is given by the complement. Then, simply put, we find what are the heads, how do we note the heads, and how do we note the tails. And that is pretty much it. So, again, I think this is it for this blot.